Hello guys, this is Chirantan Hebballi. So today we are going to look at this problem statement and simulate this problem statement in NGSpice. So this problem statement has two sub-questions. One sub-question asks us to design a 40 dB and gain of 40 dB and unity gain bandwidth of 100 megahertz fully differential amplifier, and make two copies of that and give one of them as the load to other, and to check like what is the changes, are we getting 100 megahertz, or what is the destabilization, how much it is destabilizing, and then stabilize this above circuit using a resistive common mode detector and obtain a phase margin of 70 degrees. So I'll explain common mode detector later. First, let's see how we have designed schematic at this fully differential amplifier. So this is the schematic. Here you can see. Here we have given the AC input V plus V minus and this current mirror PMOS, and then we have used Miller compensation for frequency compensation, and then uh, we have given this, made two copy of this and given load to one another. Let's look at the NGSpice code. So in NGSpice we have used TSMC 180 uh, nanometer technology MOSFET. So we are given AC inputs +1 and -1. So this X diff. So here I'll explain this dot sub circuit. This part is used to obtain a, like, make a sub circuit of this amplifier, fully differential amplifier, and then we use it using xdiff command and then give one of them as the load to another. Here I have given this power supply as 3.3 volt, and then each MOSFET is set to an aspect ratio of W by L. W is aspect ratio of 4.34 e raised to minus 6 by 0.54 e raised to minus 6. And then IDC, the current source is 20 microampere. The current source is 20 microampere, and each and every MOSFET has the same aspect ratio. And the Miller compensation capacitor value is 1 kilofarad, and we do AC analysis and plot gain and phase. So let's look at the plot. So the green one is the gain and red one is the phase. So here in green one, let's check what is the slope. We should get -3 dB, drop of -3 dB. Yeah, here you can see -7.7 dB. So it's not good. We want -3 dB. It shows us that there are two poles before the unity gain bandwidth. So to stabilize it, we have to shift the left dominant pole to the left, and then let's look at like what is GBW, unity gain bandwidth. We want it to be 100 megahertz. Yeah, you can see here it's 96. Yeah, 96 megahertz is not what we wanted. We wanted 100 megahertz. After attaching the load, we can see that this change in unity gain bandwidth, and also there's introduction of new pole, even though there was a Miller compensation. So what do we do? We use CMFB. So CMFB, what it does is it stabilizes such amplifiers. So the basic idea of common mode detecting feedback system is like it detects the common mode feedback and sets the amplifier back to common mode operating point. So here is the basic idea how it does. It takes the average of differential outputs, compares it with the reference voltage, and then gives us the input to the PMOS. So this PMOS current is like increased or decreased based on the feedback what we get, and this amplifier is set to common mode operating point. See the schematic of the above common mode detection, how it is done. So here we have used resistive common mode detection. There are also many methods like using source follower or using com using source follower and using sometimes buffer also. So here we have used resistor common mode feedback detection. So using this resistor we get common mode voltage and then give it as the give it to the input as the to the comparator here, and the reference voltage of the comparator is VDD by 2 power half of power supply. and this output of this comparator is given to the PMOS, which helps us to set the current and back set this fully differential amplifier back to common mode operating point. So let's look at what we get after common mode feedback. Yeah, after common mode feedback, we see that the left dominant pole is shifted here, and then get minus 3 dB drop. So let's see if we are getting minus 3 dB. Yeah, we are getting minus 3.27 dB, so it's approximately minus 3 dB, we can say. So here we are showed like we have shifted dominant pole and stabilized the system. Also, let's see if we are getting 70-degree phase margin. Yeah, we can see we are getting minus 108, that is nearly 72 degrees, which is like 2 degrees more. It's okay, we have better phase margin. So this is how we use this common mode feedback. Showed the simulation like how we stabilize it using common mode feedback. And also keep in mind that all the MOSFETs are of same aspect ratio, and technology node is 180 micrometer. The L and W is this. So thank you. That's what this tutorial is about, common mode feedback. And this common mode feedback is also, yeah, used in like two-stage op amp and many stages op amp to stabilize the system, which have heavy loads, which need to drive heavy loads. So that's it, guys. Thank you.